So technically we can start, but you tell me. I think we can actually start now. So I'm just going to mute everybody. Okay, so let's start. Welcome everybody to this second morning session. So we're going to have 3 talks as usual. And yeah, if you have questions, please write on the chat or raise your hand at the end of the talk. So our first speaker is Omar Fawzi, and he will be talking about tight approximation bounds for maximum multi-coverage. Please go ahead. You have to unmute yourself, huh?
Okay. Okay, so thanks a lot. So I'm going to be talking about the generalization of maximum coverage. So I'm going to give approximation algorithms for this. And yeah, so this is joint work with Sid Barman, Suprabhat Ghoshal, and Emirhan Gupta. Okay, so let me start by recalling the classic maximum coverage problem. So I'm given a collection of subsets that I'll be calling Tx of some universe, which I'll call Y, together with an integer k. And my objective is to find k of these subsets that cover the maximum number of elements possible. Okay, so in other words, I would like to find a subset S of the indices, okay, so which will be denoted by X, such that if I take the union of the sets that are labeled by the elements in S, then the size of this union is maximized. Okay, and we're going to use this notation for later, is that I'm going to denote by C of S, the size of this union. Okay, so this is typically one of the first algorithm one sees in an approximation algorithms course, because it's quite well understood. So namely, on the one hand, we have that there's a very simple greedy algorithm that one can define. So in which you just keep adding the set which covers the most elements. Okay, so you repeat the step for k times. So you get a set Sk. So in general, the set Sk will not be optimal. It will not cover the optimal number of elements, but it will be close to optimal. So in the following sense, that the number of elements that it covers will be at least a constant fraction away from the number of elements covered by the optimal set. Okay, and so and the approximation ratio here is this number 1 minus 1 over e. Okay, so it turns out that this algorithm even works more generally, not just for this coverage function that we're considering here. It works for any function, for any set function that is monotone and submodular. Okay, and this is again a classic result from the 70s. Okay, and so this is also quite nice because this happens to be tight. The simple algorithm is tight in the following sense, is that if you try to achieve an approximation ratio which is slightly better than 1 minus 1 over e, then this turns out to be NP-hard. Okay. Yeah, so as I said, so we're going to be considering here a generalization of this problem, which we'll call L coverage, that has the following property. So notice that in the maximum coverage problem, if you cover, and you take an element Y from the universe, if this element, whether it's covered once, twice, 3 times, or 10 times, it's only counted only once, right? It's counted only at most once. Okay, if it's covered by one of the elements. And the idea of this L coverage problem is to slightly generalize this. So in some settings, it might be useful to have multiple copies of a given element of the universe. And so here we'll say that an element Y is counted once if it appears once, it's counted twice if it appears twice, and up to L times if it appears L times. But then if it appears more than L times, it's counted only as L times. Okay, so that's the definition in words. So let's give a mathematical definition now. So let me, for defining this, it's useful to rewrite the coverage function slightly differently. And so one way to write it is just as the sum over all the elements Y in my universe. So I take all the elements in my universe and I look at how many times it's covered. Okay, so this is exactly the right-hand side of this quantity. So the number of x's such that y is in Tx. Okay, so if this is bigger than 1, then I count this as 1, and otherwise I count it as 0. And so the L coverage function is a natural extension of this, where I just replace this 1 by an integer L. Okay, so and then I ask exactly the same question of maximizing this notion of L coverage. Okay, so instead of finding, so I still want to find a subset S of size K, but now that maximizes this L coverage function CL of S. Okay, excellent. Okay, yeah, so let's look at the extreme cases of this question. So when L is equal to 1, of course, this is the usual maximum coverage. And as we saw in the previous slide, then there is an approximation algorithm that achieves the ratio 1 minus 1 over E, and this is optimal. Okay, so on the other hand, on the on the other extreme, so if I take L equals infinity, then I have no bound at all on the number of times that an element, that I count an element. So this becomes a simple problem, in the sense that the C infinity of S is just the sum of the sizes of the set that I take. Of course, algorithmically, this is a trivial problem. I can solve it trivially, so I can, of course, have an approximation ratio of 1 in polynomial time. Okay, and so the question we're asking here is between these two extremes, like this very simple extreme and this very well-known extreme, what happens for other values of L? Okay, and so our main result is basically a characterization of this optimal approximation ratio for all values of L. Okay, so for doing this, we give a polynomial time algorithm, approximation algorithm that achieves an approximation ratio given by this quantity rho L. And on the other hand, we give a matching hardness that shows that you cannot achieve an approximation ratio that is better than rho L plus epsilon. Okay, so I notice here that it's a unique games hardness, not an NP hardness. Yeah, we were not able to show the NP hardness. Okay, so yeah, so just a few comments on this factor rho L. So of course, as expected, for L equals 1, it gives 1 minus 1 over E, but then it improves as L grows, right? So for example, rho 2 gives you 0.73, and this increases and it goes to 1 as L goes to infinity, and at a rate which is roughly 1 over square root L. Okay, so this is the main result, yeah. So I guess the problem is quite natural enough. It doesn't need much motivation, but still, I want to. I think it's useful to give you my perspective, my motivation on studying this question, because I actually come from information theory, more precisely quantum information theory. And so this is where, from where I got interested in defining and studying this problem. Okay, so let me give you a bit of background on this. So yeah, so in information theory, one of the main questions that we study is we have a noisy channel. Let's say between two parties, and my objective is to achieve reliable communication between them. And so for this talk, I'll be modeling this noisy channel as just a conditional probability distribution. So for every input of the channel X, I'll have a probability distribution on the outputs, which I'll be calling Y. So W of Y given X is just the probability of seeing Y as output if the input is X. Okay, and my objective is using this noisy channel is to be able to communicate a message between the sender, which I call Alice, and the receiver, Bob, okay, which will be just an element between 1 and K. Okay, so my objective is to design a system that uses this noisy channel in order to communicate this message I. Okay, so how do we model this? Yeah, so the encoder is just a function from the message space to the set of inputs of the channel, which I denoted by X, and the decoding function is just takes an output of the channel to an element from 1 to K. Okay, and my objective is to, of course, yeah, so the success condition is that whatever is decoded from Bob's side, what I call J, is the same as whatever Alice wanted to send. It's J is equal to I. Okay, and my objective, my variables here and my optimization are the choices of this encoder and decoder. Okay, and I want to maximize the probability that I is equal to J. Okay, so I have to put a distribution on I, so I put a uniform distribution on the message, not a very important detail. Okay, and so I can rewrite this problem. It's easy to rewrite this problem as follows. So I want to achieve the optimal success probability for sending K messages over the noisy channel W. And so I can write it as follows, as okay, up to some constant, up to some factor, this factor 1 over K. It's a maximization over all possible subsets of X of size at most K of some function of S, some set function of S. And this set function has the following property. It's a sum over elements Y of the maximum over X in S of the probability of the output being Y, condition on X. Okay. So yeah, if you're a bit familiar with covering function, you see that this is nothing but a kind of weighted coverage function. But if you want to see it more explicitly, you can look at the special case of a channel where for every input X, the output is uniformly distributed on a given subset, okay, which I call Tx, okay? And then it's easy to see that this function just becomes the following. It becomes up to this, this factor 1 over T, it just becomes the size of the union of the sets Tx, okay? Which is exactly this coverage function that we had at the beginning of the talk. Okay, so the bottom line of this is that an optimal coding strategy for a given noise model is a weighted maximum coverage problem. Okay, and actually we use this in this paper, and we had some applications of this, in particular just on how entanglement can help for the transmission. Okay, good. So where did this L coverage come from? It comes from looking at the natural variant of this coding problem, which is natural from an information theory point of view, which is this list coding problem. Okay, so here it's exactly the same setup, except that now what Bob does, I mean, we relax a bit the condition of the decoder. So the Bob outputs, instead of outputting a single J, he outputs a list of L J's. Okay, and the success condition is now that the true message I is an element from this list. So that's called list coding. And now you can, of course, rewrite this optimal success condition in a very similar way, except now this function, which we call f of c, is now, I mean, it's very similar, except this maximum, instead of being just the maximum element from a given list of elements, it's you take the L largest ones and you sum them. Okay, and so this again, similarly to before, it's a weighted version of the maximum L coverage problem. Okay, so again, optimal list decoding corresponds to a weighted maximum L coverage problem. Okay, so yeah, that's it for the motivation and where how we came up with studying this problem. So let me now get back to the problem that we're studying and tell you what our approximation algorithm looks like. Okay, so again, this is so I want to find K subsets that maximize the L coverage. Okay, and I want to achieve an approximation ratio, which is given by this factor rho L. Okay, which is, yeah, so let me read it once. So 1 minus L to the L, e to the minus L divided by factorial L. And so, yeah, it might seem a bit strange, and it has a simple probabilistic interpretation, which I wrote here. So it's given in terms of the expectation of some function applied to a Poisson random variable with a parameter L. Okay, so before getting into the actual algorithm we use, let's make some simple observations about this problem. Is that, so the function CL, the L coverage function, is a submodular function for any value of L even. So this directly implies that if I run the greedy algorithm, then I will achieve a factor of 1 minus 1 over E. Okay, so a simple observation, but of course the point here is that I wanted to achieve an approximation ratio which is better than 1 minus 1 over E, because this function has more structure. Okay. The second observation is that actually the greedy algorithm cannot achieve an approximation ratio which is better than 1 minus 1 over E. Okay, and the basic idea to see this is that if you start with an instance where the greedy algorithm is not very good, then you can construct another instance for L coverage by duplicating each of the sets L times. Okay, and this, you'll see that it will be an equally bad instance for the greedy algorithm for L coverage. Okay, so I just put a simple instance here where you duplicate, you have the sets 1, 2, 3, 4, and 2, 3 duplicated 2 times. And so the greedy algorithm will, or can pick, let's say, the set 2, 3, and then 2, 3 again, and then 1, 2, and then 1, 2 again. So this will achieve basically as good as the greedy achieves on the original sets. Okay, so we have to go beyond the greedy to improve this factor. Okay, so this is the second observation. The third observation is that one could try using some other notion. So notice that, yeah, that this function CL kind of interpolates between the coverage function and a completely linear function. Okay, so one could try to use this notion of curvature, which is studied in the context of submodular optimization. But unfortunately here it cannot be used. So because this function, this L coverage function has a trivial curvature. So it will not give you anything better than 1 minus 1 over E. And the reason for that is, for those who are familiar with this, is that this, this L coverage function, is bounded at some point. At some point it will not increase anymore. Whereas functions with a non-trivial curvature can always increase in some sense. Okay, so yeah, these are the things we cannot do. Okay, so the algorithm we use instead is another standard idea in this area, is to consider the natural linear programming relaxation. Okay, so the natural linear programming relaxation is as follows. So instead of just for every element x, I put the 0, 1 variable, whether I take x in my set S or not. I consider a variable which is between 0 and 1. Okay, so and this variable ry is saying how many times I cover the element y. Okay, so of course ry should be smaller than the sum of the px's that contain y. Okay, so this is just a very natural LP relaxation. Okay, so yeah, so how does my algorithm work is that I first write down this LP relaxation, I solve it, I get these optimal solution, P stars and R star, and then I use another standard technique in this context is to called the pipette rounding, which allows us to transform this fractional solution, P star, into an integral solution, which satisfies the following properties. So first, of course, it's integral. And but then it's also feasible in the sense that the sum of the px is equal to k in this setting, and okay, and also that I can relate so okay, of course p int is integral, so I can evaluate the L coverage function on it, and so I can find a lower bound on the value that this that this p int takes, and it's lower bounded, yeah, so not by the LP value, but by the expected L coverage for a set S constructed at random using P star, okay, using the P star I started with. And so the way S is constructed is very natural, is I take every element X and I include it in the set S with probability given by this P star X. Okay, so in order to finish the analysis, basically what I have to do in order to analyze this algorithm, and of course, okay, what I output in my algorithm is this p int, the set defined by p int. Okay, so what I have to analyze in order to analyze my algorithm is how good is this expectation over S of the L coverage of S. Okay, so yeah, once I do this, so and this is what is written here in the middle of this of these set of inequalities in blue. So if I manage to lower bound this expectation in terms of the value of the LP, okay, so by some factor which is given by rho L, then of course this LP I can relate it to the value of the optimal. It's always bigger than the optimal, and using this property of pipette rounding, I can relate the expectation to the value returned by the algorithm. Okay, so what remains to do is to prove this blue inequality. Okay, so how do we do this? So let me focus in this slide on the L equals 2 case. And I'll go a bit quickly. So yeah, so first, by linearity of expectation, I can focus on a single y, right? So notice that on the left-hand side, it's a sum over the elements in y, and on the right-hand side as well, so I can focus on a single y. Okay, and so I want to compute the expectation of this quantity, which is the minimum of 2 and the number of times I cover y. Okay, but notice that this number of times I cover y is a random variable here, because my set is random, and it's given by a sum of these indicators. Okay, so let's just for simplifying the presentation, I'll assume that these px, which come from my LP, are just take two values, either 0 or q, let's say. Okay, then in this case, the sum of indicators has a binomial distribution with some parameters, t and q. And so I can actually compute this expectation. Okay, so I can compute it as a function of q and t. Okay, and then I use some monotonicity properties and together the fact that I mean the relation between the constraints of the LP to relate qt and the variable ry. Okay, so this is what gives me the second this first inequality. Okay, and then using just the right the convexity of the right functions, so I can transform this expression, which is nonlinear in ry, into something which is linear in ry at the cost of getting this prefactor, which is exactly the ratio we wanted. So it's 1 minus 2 e minus 2, which is exactly rho 2. Okay, so this is basically how the analysis works at the high level for L equals 2. For general L,
just Omar, 4 minutes left.
The complication might be a bit more. The computation might be a bit more, and will be a bit more complicated for general L. So here it turns out that there's a very nice tool that we discovered during this project. So I just want to talk about it briefly. Is this notion of convex order between distributions? Okay, so here for our special case, it allows us to compare between binomial distribution and a Poisson distribution. And by basically saying that the Poisson is more spread than the binomial distribution. So, and the way this is modeled is by saying that for any concave function g, so here we apply to the concave function, which is the minimum of L and identity. So it's this function which is like this. So this is the concave function. We can relate the expectation of g applied to a binomial to the expectation of g applied to a Poisson. Okay, and by using this notion together with analysis similar to what I presented before, we can get the desired results. Okay, so yeah, let me okay, very briefly I say a word on the hardness of approximation. So for that we use so as I said, we do the reduction from unique games. So we use a version of unique games which is based on a hypergraph version of the unique game problem. So let me not go over this. And yeah, so of course what we want to do is to go from an instance of this hypergraph unique games to an instance of this maximum L coverage. And for that we use, as is done in the proof of FIGO, we use this partitioning gadget, which is now adapted for this notion of L coverage. Okay, and then, okay, so let me conclude. So yeah, so we consider this notion of maximum L coverage, this maximum L coverage problem, and we gave a tight polynomial time, I mean, we gave a polynomial time approximation algorithm, which achieves an approximation ratio, which is rho L, and a matching hardness. Okay, so one quick comment I can mention here is that if you look at the set cover version of this problem, in the sense that you want to cover everyone and you want to pick the minimum number of sets that covers everyone, then actually the L cover is as hard as set cover, okay, for some version. Okay, so I think, yeah, so I'm quite interested in this interplay between information theory and approximation algorithms. And there are many open questions there, but for being concrete, let me just mention one open question is can one find a combinatorial algorithm that achieves this same ratio rho L, or even just beating the simple 1 minus 1 over E bound? Okay, for this maximum L coverage, even for L equals 2. Okay, let me stop here. Thank you.
Thank you very much for a nice presentation. Are there any questions? Yes, I have one from Stavros. If you want, you can unmute yourself and ask.
Okay, sure. Thank you. Well, the question is just if you have the upper bound now, the number of times you can choose a set is 1, right? So if you're given a bound of D, which is different for every set, which is the bound of D greater than or equal to 1. So essentially you're choosing, you know, you can choose many times a given set. The same analysis works, or I guess it would work, but
you're meaning that yes. I mean, so I mean, this can be a special instance where just you have multiple times the same set.
Okay.
Yes, this works.
So as simple as that.
Yes.
But okay, this is pseudo polynomial, right? So this is part of your input, these upper bounds. So
you're meaning
so it's a parameter given in the problem definition, right? This D for every set. So what you suggest is pseudo polynomial reduction. So
okay, yeah. So yeah, if now your number D is super polynomial in the instance size, yeah, then I don't know, but
which maybe, yeah, okay.
But then yeah, but then actually I don't know. But then you can replace it. I mean, if it appears too many times, then I mean, it's never useful to have it more than the number of times in your universe. Yeah, so I think you can bound the number of times a set ever appears polynomially. So I think this could be handled.
Okay, good. Are there any other questions? Okay, I don't see any hand raised. In that case, I can unmute everybody. And I mean, everybody can unmute himself and give a round of applause.